Welcome to lesson number 8. With this lesson, we complete our description of the activity coefficient for components in a mixture. And in general, we complete our description of the thermodynamics of mixtures, for as much as it is required to develop a fully real thermodynamic model of gas melt equilibrium in magmas. This lesson is going to be longer than the previous ones, but you can stop it, of course, at any point. Take your time to digest the concepts, then restart it, and do it as many times as you wish. Let's start with a one-slide recap of the previous lessons. We have discussed what happens when we mix individual components into a mixture. And particularly, we have been examining volume and entropy as they result from mixing together individual components. Volume and entropy are important because they contribute to define Gibbs energy. And we know that for any given pressure and temperature, minimization of the Gibbs energy is the criterion for equilibrium. If you need a refresh on that, we saw it in lesson 1, while in lesson 2 and 3, we demonstrated that minimization of the Gibbs energy corresponds to both equality of the chemical potentials and equality of the fugacities. One involves the other for each component in all phases. From the analysis on volume and entropy of mixing, therefore, or the Gibbs energy of mixing, we found an expression for the activity coefficient of a component in a mixture, which relates to the partial molar excess Gibbs energy of the component. Therefore, in order to describe the activity coefficient, we need an expression for the excess Gibbs energy of the mixture. This will be, in fact, the content of this lesson. In lessons 6 and 7, we have repeatedly said that the activity coefficient is intimately related to the definition of a reference state. In fact, the activity coefficient combines with the reference fugacity to describe the fugacity of the component. Given a reference state, the activity coefficient describes the deviation from the reference state due to the actual conditions of the system different from those of the reference. In lesson 6, we have seen how to describe the reference fugacity in terms of only a reference volume. And we have defined such a reference as that of a hypothetical pure dissolved volatile. We delayed the definition of the reference volume for each hypothetical pure dissolved volatile to when the activity coefficient would be defined, as the two, once again, depend on each other. We said, however, that a smart choice is that of giving the reference state the duty to account for pressure and temperature by letting the activity coefficient account for the actual liquid composition. We have, in these slides, all of the fundamental elements that concur to define the fugacity of a dissolved component. That will be given by a constant quantity defined for each dissolved volatile at a given pair of pressure and temperature, P0 and T0. A series of integral terms that depend on a reference volume, still to be defined, and that move the reference conditions from P0 and T0 to system pressure and temperature, and an activity coefficient that depends on the excess Gibbs energy and takes into account the real composition of the liquid, moving the conditions from those of the reference state at system pressure and temperature to those of the liquid with its effective composition. Once again, The roles of pressure and temperature are absorbed by the hypothetical pure dissolved volatile that we adopt as a reference, while the excess Gibbs energy takes care of the effective melt composition. Accordingly, the volume of the hypothetical pure dissolved volatile must depend on only pressure and temperature, whereas the excess Gibbs energy must be a function of the composition of the melt. You may understand that I am a fan of the old Latin saying repetita juvant, repetitions help. Now I think the picture is clear. What we need to define to complete our description is a pressure temperature dependent volume for the hypothetical pure dissolved water and hypothetical pure dissolved carbon dioxide. And we have to define a composition dependent excess Gibbs energy for silicate melts, including the dissolved volatiles. With such expressions, the equations in this slide will lead us to compute consistent reference fugacities and activity coefficients for water and carbon dioxide dissolved in silicate melts. And with that, our real multi-component volatile saturation model will be complete. Let's talk first of the volume of the hypothetical pure dissolved volatile. In the case of water, we can count on a substantial experimental and theoretical work by the great petrologist Wayne Burnham and his co-workers on albedo melts developed from the 60s to the early 90s of the last century. Through that large work, Burnham was able to determine a pressure-temperature dependent expression for the partial molar volume of water dissolved in albedo melts that you see in the slide. Well, that's perfect for us. We are looking for a pressure-temperature dependent hypothetical state of pure dissolved water. That corresponds to a sort of neutral state on which the compositional effects would then be added through the activity coefficient. We can therefore use as a neutral state from which to determine the reference fugacity the state of water dissolved in albedo melts and take its pressure temperature dependent volume as that of our hypothetical pure dissolved volatile. Such a state is sufficiently close to the ones we are interested in, that is, the state of water dissolved in silicate melts of variable composition. Therefore, we can safely assume that such a reference state represents a reasonable starting point from which to just compute deviations as due to the effective liquid compositions. Deviations that we compute through the excess Gibbs energy and the activity coefficients, which depends on it. That holds well for water. But what about carbon dioxide? Unfortunately, we don't have a similar relationship for carbon dioxide. That is, we don't have a robust pressure, temperature dependent partial molar volume of carbon dioxide for some silicate melt composition that we can adopt similarly as we do for water as representing our hypothetical pure dissolved state. This volatile component, carbon dioxide, and its interactions with silicate melts haven't been studied so deeply as Wayne Burnham did for water. What we can do is to assume a form similar to that of water, however with unknown parameters, then employ the bulk of saturation data involving carbon dioxide to determine by regression the unknown coefficients. In fact, The first formulation of the model in the 90s included an equation of states for the hypothetical pure dissolved carbon dioxide involving 10 adjustable model parameters analogous to the A parameters that appear in the equation for water in this slide. However, the parameters for water are known from the work of Burnham, whereas those for carbon dioxide are not known, and we had to calibrate them through regression of the carbon dioxide solubility database. That increased substantially the number of model parameters, which is not a good fact, especially when the data in the database are not particularly abundant, and they were not in the 90s for carbon dioxide. We must keep instead to a minimum the adjustable parameter so as to minimize data overfitting and increase the robustness of the model. In a subsequent model revision published in 2006, we employed, during database regression, progressively simpler forms for the reference molar volume of dissolved carbon dioxide, and finally selected the simplest form that turned out to be sufficient to reproduce the database to an acceptable approximation. This is the form that was employed at the end. It is extremely simple, and it involves only a linear dependence in temperature and pressure, and only 3 parameters indicated with the symbol B that are calibrated down from the database. I will talk extensively later on in this lesson of the relationships between the real systems and their modeling counterparts. By now, it is important to note that when developing a model, the degree of complexity should be the one that is necessary for the modeling purposes, and nothing more than that. That concept will become much clearer in the following. So by now, just take the ideas that have been introduced in these slides and know that we will get back to them later on. With the definition of the reference molar volumes, the very last step remaining is the definition of the excess Gibbs energy of the melt. Once we have it, we can compute its partial derivative with respect to the number of moles of dissolved water or of dissolved carbon dioxide and obtain the activity coefficient of each dissolved volatile. Because the Gibbs energy carries all of the roles of the effective silicate melt composition, we expect it to depend strongly on composition. In many such problems, it is common to express the excess Gibbs energy of a mixture as an expansion in terms of binary interaction parameters. That was introduced first in 1895 by Max Margules, and for that reason, the binary interaction parameters are also called the Margules parameters. And this approach to model the excess Gibbs energy of mixtures is called the Margules activity model, or more simply, the Margules model. Here, the Wij parameters express in an effective way the attractive and repulsive forces originating from each pair of components in the mixture. The binary interaction parameters, Wij, can be symmetric, meaning that the interaction of the component I with the component J is the same as the interaction of the component J with the component I. Or they can be non-symmetric. In the first case, the interaction between the components I and J is described by just one coefficient, while in the second case, that of non-symmetric binary interaction parameters, that interaction is described by two coefficients. The excess Gibbs energy can also be expressed as an expansion in terms of interactions involving not just pairs, but also triplets, or even higher order interactions between the components, implying a progressively higher complexity in the description of what we call the topological properties of the Gibbs energy. You can think of the Gibbs energy of a mixture for any given pressure-temperature pair as a complex surface in a multidimensional space defined by the number of individual components describing the mixture. For example, for a silicate melt made of 10 major components plus 2 dissolved volatiles, that results in a surface in a 12-dimensional space. Quite hard to imagine and to imagine. The aim of equilibrium thermodynamics is that of finding the absolute minimum of such a surface, that is, the combination of quantities on the 12-axis that results in the minimum value of the Gibbs energy. That corresponds to thermodynamic equilibrium, as we know from lesson 1. And it also corresponds to a quality of fugacities for the components in the various phases, as we know from lesson 3, and as we have been employing as a thermodynamic equilibrium equation throughout this training module. In principle, the functional form of the binary interaction parameters Wij is not known a priori. The parameters can be constant numbers or more complex functions of pressure and temperature. The functional form of the binary interaction parameters has strong implications in terms of mixture modeling. That should be clear to us by recalling the relationships between Gibbs energy, volume, and entropy, and in particular, their excess parts that describe the results of the attractive repulsive forces acting between the components in the mixture. Let's focus on volume first. Volume is the pressure partial derivative of Gibbs energy, and similarly, the excess volume is the partial pressure derivative of the excess Gibbs energy. Consider the case where the binary interaction parameters do not depend on pressure. In such a case, the excess Gibbs energy does not depend on pressure, and the excess volume of the mixture turns out to be equal to 0. On the contrary, if at least some of the binary interaction parameters depend on pressure, then the pressure partial derivative of the excess Gibbs energy will be non-zero, implying the existence of an excess volume. The reasoning is entirely similar for the temperature dependence of the binary interaction parameters. If such parameters do not depend on temperature, then the excess entropy of the mixture is 0, while it will be non-zero in the opposite case. Note here that the concept of real mixture, that is, a mixture with non-zero excess Gibbs energy, does not imply necessarily non-zero excess volume of entropy. In fact, consider the case where the binary interaction parameters in the expression of the excess Gibbs energy are pressure and temperature independent. That is, they are just constant quantities for each binary interaction between the components in the mixture. In such a case, the excess volume and excess entropy are both equal to 0. Still, there is an excess Gibbs energy, and when partially derived the number of moles of a given component, that results in an activity coefficient of that component, which will be in general different from 1. A similar mixture is said to be of the scattered Hildebrand type, and it is also referred to as a strictly regular mixture. A strictly regular mixture is therefore a mixture where the binary interaction coefficients are independent from both temperature and pressure. If the binary interaction parameters involve a temperature dependence but no pressure dependence, then the excess volume would be equal to 0, meaning that the components mix without varying their volumetric properties. That is called, accordingly, an isometric mixing model. The reverse case, in which there is an excess volume while the excess entropy is 0, is called regular non-isometric model. Finally, a non-regular non-isometric model has both non-zero excess entropy and volume, implying both pressure and temperature dependence of the binary interaction parameters. It happens to find all of these different classes of models referred to in the literature as regular solution models, although, strictly speaking, a regular solution is only the first one in this list, that is, the one with binary interaction parameters represented by just one pressure-temperature independent coefficient. Once again, in all of the above cases, the activity coefficients are in general different from 1. The concepts just introduced here and that illustrate the relationships between the specific functional form of the binary interaction parameters and more generally of the excess Gibbs energy and the properties of the mixture, is fundamental in mixture thermodynamics. Let's have a closer look at it, and let's focus on the simpler case of volume, which will bring back into discussion our molar volume for the reference state that we have seen a couple of slides back. While we focus on volume, the arguments are entirely general and hold in a similar way for entropy, enthalpy, and any other thermodynamic mixture quantity. We consider the partial molar volume for a generic component I, for example, of volatile components such as water or carbon dioxide. Let's then consider the partial molar volume of the dissolved component water. As we know well, the partial molar volume of a component is the partial derivative of total volume in the number of moles of the component. In turn, volume is the pressure partial derivative of Gibbs energy that we can substitute in the equation. From here, simply apply the Schwarz identity that we introduced in lesson 6 and change the order of the partial derivatives. Now we have the partial derivative of the Gibbs energy in the number of moles of dissolved water, and results should then be partially derived in pressure to finally obtain the partial molar volume of dissolved water. This is the general expression for the Gibbs energy of a mixture that we have derived in the previous lesson 7. Let's then apply the partial derivative in the number of moles of dissolved water. The first term in the expression that we obtain is the reference chemical potential. I haven't developed the Gibbs energy of ideal mixing term and the excess Gibbs energy term. For the moment, I have just reported their partial derivatives in the number of moles of dissolved water. We can then substitute this expression into the equation on top. Now, let's recall the differential of the chemical potential for a pure component, from which we know that the partial derivative of the chemical potential is molar volume. Let's then apply the partial pressure derivative in the equation on top. Really, the ideal mixing term disappears, as we know from the previous lesson that the ideal mixing term is not a function of pressure. Therefore, upon pressure derivative, it gives a zero result. We finally obtain the expression for the partial molar volume of dissolved water that we were looking for. Let's look at it in this new slide. The partial molar volume of dissolved water is given by a reference term plus an excess term. The reference molar volume of dissolved water corresponds, in our case, to the partial molar volume of water dissolved in liquid albite. Let's look at the excess term. The internal derivative is done by keeping constant the number of moles of all components except water. Therefore, it makes all the terms that do not involve water disappear. The pressure derivative is therefore applied to only the terms that involve dissolved water. If those terms do not involve any pressure dependence, then the whole excess term is zero. We can now fully understand the global reasoning behind the model. We know the partial molar volume of water in a specific silicate melt, liquid albite. We have adopted that quantity as the reference partial molar volume of water dissolved in any silicate melt. Then the excess Gibbs energy, and in particular the part of it which depends on water, gives us the deviation from such a reference partial molar volume as due to the composition of the specific melt under consideration. If that deviation exists, that will be reflected in the pressure dependence of the binary interaction parameters involving the dissolved water. Instead, pressure-independent binary interaction parameters involving water would imply that the partial molar volume of water in the melt under consideration is the same as the partial molar volume of water in albedic melts as described by Burnham. We now start to see the overall consistency of the model. I showed the case for partial molar volume, but the same holds for any other thermodynamic quantity, like partial molar entropy, partial molar entropy, and activity coefficient, which relates to partial molar Gibbs energy. Each of these quantities relates to the excess Gibbs energy. Therefore, a proper form for the excess Gibbs energy of silicate melts, and in particular for the interaction between volatile components and silicate melts, requires that a variety of thermodynamic data be evaluated. In fact, partial molar volumes constrain the pressure dependence of the excess Gibbs energy. Partial molar entropies and entropies constrain the temperature dependence of the excess Gibbs energy, and volatile saturation data, which depend on the activity coefficients, constrain in principle all the terms, including the pressure temperature independent terms of the excess Gibbs energy. A complete and consistent thermodynamic model of volatile silicate melt interaction, allowing the calculation of the effects of volatile components on the thermodynamics of silicate melts, requires such a rich availability of data, as each group of data provides constraints on different aspects of the excess Gibbs energy. If you are interested in silicate melt thermodynamics, and if you are looking for your own research theme, here is a great area for future developments. Let's start the systematic production of thermodynamic data tailored to the definition of a complete expression for the excess Gibbs energy of volatile bearing silicate melts. Now you have all of the knowledge necessary to understand what data you need why you need them, and how those data combine to constrain a complete formulation for the excess Gibbs energy. That is clearly a career-long endeavor, but it can be a highly rewarding one, as volatile components, their interactions with silicate melts, their capability to profoundly alter the properties of silicate melts, all of them have huge impacts in the science of volcanoes, in geothermal energy applications, and virtually in any industrial application involving silicate melts, such as in the industry of glass or in that of the ceramics. As for today, we must unfortunately accept a largely suboptimal situation. We have, fortunately, relatively many data on volatile solubility and saturation, especially for water, followed by carbon dioxide, then by sulfur, and much less for other typical magmatic volatile. That's particularly relevant because, at least in principle, solubility and saturation data can constrain the overall form of the excess Gibbs energy. Case for other types of data is much less satisfactory, as we only have sparse data on volumes, enthalpies, and entropies of volatile bearing silicate melts. And quite often, they are model-dependent estimates instead of being directly measured quantities, making them scarcely useful as an effective, robust constraint into a general model of volatile bearing silicate melt mixtures. In practice, what we do is to rely on just the solubility saturation data. If you don't remember why I continue to distinguish between solubility and saturation, just have a look back to lesson number 4 and you will find the distinction. So we employ the solubility saturation data to constrain by standard regression techniques the minimum functional form required for the excess Gibbs energy. And we use them to estimate the corresponding parameters. How many model coefficients do we need to estimate? Not first of all that I use the term coefficients and not parameters to refer to quantities represented by numbers and that are constrained by regression of some datasets. That is done in order to avoid confusion with binary interaction parameters, the Wij quantities that we have seen, and which can display various forms of pressure-temperature dependence. Therefore, they can include various coefficients in their functional form. So, with this in mind, how many coefficients do we need to constrain? Let's refer to the general equilibrium equation that we have here. On the left-hand side, we have nothing to estimate, as the fugacity coefficients appropriate for water carbon dioxide mixtures over the pressure temperature conditions of our interest are known from previous work. We have discussed that abundantly in lesson number 5. On the right-hand side, which deals with the liquid part of the equilibrium, the situation is unfortunately less favorable. We have seen in lesson 6 that we must first of all estimate the reference fugacity of each volatile component for a pair of reference pressure temperature conditions that we also don't know in principle, but that we can define without the need of estimating them through regression. Furthermore, we have seen in this lesson that we need 3 coefficients defining the reference volume for dissolved carbon dioxide. That makes up 5 coefficients, which is largely manageable. However, things become much less manageable when referring to the activity coefficient, which depends on the excess Gibbs energy. In fact, here we have a series of parameters describing binary interactions between any pair of components in the liquid phase, such as silica, aluminum, titanium, water, carbon dioxide, sodium, and so on and so forth. And such parameters can, in principle, contain a series of coefficients, depending on their specific pressure-temperature dependence. For 10 major oxides plus 2 dissolved volatiles, water and carbon dioxide, that makes up 66 binary interaction parameters times the number of coefficients in the functional form. Compared with the available data on water and carbon dioxide solubility and saturation in silicate melts, that's far too much, opening to a high risk of overfitting. Of course, if we increase the model coefficients, we fit the data better. If we increase the number of coefficients to correspond to the number of data, the correspondence between the model and the data becomes perfect. But such a model does not have any value, because when used for conditions not coinciding with those in the database, it produces numbers without any physical meaning. There are statistical methods to ascertain whether the number of model coefficients estimated by data regression is adequately low. In general, at equal model performance, the less the number of model coefficients, the more robust the model, or the higher the likelihood that model extrapolations outside the range of the data produce reasonable results. Thus, we want to keep the number of model coefficients as low as possible, and certainly lower than the large numbers from the figure in this slide. How can we do that? As for a number of other steps in model development, we can fortunately rely on previous work by other scientists. From the 80s of the last century to just recently, Mark Ghiorso and his co-workers have developed substantial thermodynamic modeling of silicate melts. Their approach is similar to the one developed along this training module. As we do here, they treat the excess Gibbs energy as an expansion in terms of symmetric binary interaction parameters that they assume to be constant numbers. With the aim of modeling the complex pressure temperature composition dependent crystallization paths of silicate melts, they have employed quite large data sets and have constrained by data regression the binary interaction coefficients. More recently, they have extended their approach to include water and carbon dioxide. But that's not what we are interested here. What is important for our developments is that we can rely on substantial previous work to significantly lighten our tasks. In fact, what we can do is to employ the coefficients of interaction between all possible pairs of non-volatile components in silicate melts, described by 10 major oxides, and concentrates our efforts in estimating, through regression of the water and carbon dioxide saturation data, only the parameters involving these two volatile components. That makes our job easier, since now the Wij parameters that must be determined by regression of the database decrease in number from 66 to only 21, 10 for the interaction between water and each other major component, such as silica, alumina, and so on, 10 for the similar interaction between carbon dioxide and each major component, and 1 for the intervolatile interaction, that is, the interaction between water and carbon dioxide. There will be a Wij parameter describing the interaction between the dissolved volatiles, of course. These parameters might be each corresponding to a constant number, like in the Scatchard-Hildebrand or strictly regular solution models, or they may each involve more coefficients if they turn out to be dependent on pressure and temperature. That is, if the dissolution of volatiles in silicate melts implies the emergence of excess volume and excess entropy and enthalpy. Well, our long journey from the fundamentals of mixture thermodynamics to the development of a real model for multi-component volatile saturation in silicate melts is nearly getting to an end. After that, it will be a matter of exercising with the SOLVE-CAD code, which implements all of the equations developed so far, and those that we are up to see in the next few slides. We just said that the binary interaction parameters involving dissolved volatiles might be just constant numbers, that is, simply equal to a coefficient, or they might be a function of pressure and temperature, therefore involving multiple coefficients. Each one of the possible forms for the binary interaction parameters has consequences for the thermodynamics of volatile bearing magmas, involving or not involving an excess volume, excess entropy, or excess enthalpy. However, one other concept must be introduced, and this is a very relevant one when doing whatever kind of physical mathematical modeling. A model is only functional to its purposes. What's the meaning of this? With respect to our specific problem, the meaning is that the functional form of the binary interaction parameters that we need to employ in our model of real multi-component water carbon dioxide saturation in silicate melts is only functional to the purpose of representing with a sufficient accuracy water carbon dioxide saturation in silicate melts. We have seen that such a form has consequences on mixture volumes, entropies, enthalpies. However, we shouldn't expect the model to be equally accurate in reproducing such quantities, because representing those quantities is not among the purposes of the model. Clearly, a complete, internally consistent model would be able to reproduce all those quantities correctly. But we have seen that such a purpose requires a much larger variety of data, such as volume data, entropy data, enthalpy data, that we do not have with the required abundance. We can only rely on abundant water and carbon dioxide saturation data. Therefore, we expect our model to be able to represent with sufficient accuracy water and carbon dioxide saturation, and not necessarily other quantities, although those quantities are in principle represented by the model. In other words, quantities such as volume, entropy, enthalpy are only as much accurate as it is required by the aim of computing volatile saturation. These concepts are fundamental to properly understand the modeling approach. Discussing these aspects further and showing them through operation and calculations will be highly instructive, but it would bring us away from our objective, which is that of obtaining expressions for the activity coefficients of dissolved volatiles, the last quantity that we need in order to complete our real multi-component saturation model. So just let's go back to it. And to do that, let's go back to our problem of determining the functional forms and the coefficients of the binary interaction parameters involving water and carbon dioxide. And together with them, the other quantities that must be determined by data regression, that is, the reference fugacity of water and of carbon dioxide, at a pair of P0 and T0 values appropriate for each volatile, and the coefficients in the expression of the reference volume of dissolved carbon dioxide. This slide shows the database over which SolveCAD was calibrated in 2006. As you can see, there are many more data on water than on carbon dioxide solubility, and not so many data on water plus carbon dioxide saturation. However, altogether, they make a regression matrix with more than 1,200 entries, which will turn out to be more than a factor 40 greater than the number of estimated model coefficients. We are particularly interested in a model capable of accounting for the compositional variability of silicate mass. The figure here shows that such a variability is well represented in the database. Besides that, the pressure and temperature ranges of the data are also wide, extending much beyond the conditions for most applications of volcanological interest. We still need to understand how to determine a proper functional form for the binary interaction parameters involving water and carbon dioxide. Well, what we did was to employ several possible forms, from the simplest one represented by simple coefficients to more complex ones involving various forms of pressure-temperature dependence. Then employ statistical methods to identify the simplest form that is sufficient to reproduce the database with satisfactory accuracy. I do not enter the statistical aspects of the regression procedure and all of these satisfactories that I used in the sentences above, as that would require another dedicated training module. It is sufficient here to understand that we let the data themselves tell us what form to adopt. Clearly, that form might change in the future when more data with increased accuracy will be available. That is one crucial aspect of classical thermodynamics, which employs data to calibrate models. No model can be better than the data it employs. Models can be as good as allowing us to interpolate and even extrapolate from the data in a physically robust way. But if the data they employ are poor, the models are also poor. The usual way of saying is garbage in, garbage out. In other words, the data are fundamental. Fortunately, in our case, the data are not that bad. And many more have been produced more recently, which stimulates towards a next database regression and model update. By employing the data together with the model that we have been developing so far, two different functional forms for the binary interaction parameters emerge for water and for carbon dioxide. In the former case, that is for water, the database turns out to be satisfactorily reproduced by just employing constant binary interaction coefficients. On the contrary, for carbon dioxide, some form of pressure dependence of the binary interaction parameters turns out to increase with statistical significance the model performance in terms of reproducibility of the database. We will discuss it more in a moment. By now, let's just focus on the resulting number of model coefficients estimated by data regression. The database is such that titanium and magnesium oxides turn out to be underrepresented and not providing numerical stable coefficients. As a consequence, the model simply assumes a value of 0 for the corresponding binary interaction parameters involving water and carbon dioxide. Finally, the intervolatile interaction parameter, W water carbon dioxide, turns out to have statistically negligible effects. Therefore, it is also given a value equal to 0. At the end, the number of model coefficients determined by data regression is only 9 for water, given by 8 binary interaction coefficients, plus the reference fugacity at P0 and T0, and it is 20 for carbon dioxide, given by 16 binary interaction coefficients, plus the reference fugacity at P0 and T0, plus 3 coefficients determining the reference volume for dissolved carbon dioxide. We are, finally, in the position to determine expressions for the activity coefficient of each dissolved volatile, the end of our journey. The activity coefficient is the partial derivative in the number of moles of the excess Gibbs energy. In turn, the excess Gibbs energy is described as an expansion in binary interaction parameters, and we have come to the conclusion that the binary interaction parameters are simple coefficients when they do not involve volatiles and when they do involve water, while they are expressed as a function of pressure when they involve carbon dioxide. We can therefore operate the partial derivative and finally obtain the activity coefficients of dissolved water and dissolved carbon dioxide. These are the resulting expressions, where we have expressed the non-volatile part of the liquid composition according to the expression at the top right corner. That expression normalizes the sum of non-volatile mole fractions to 1, so the expression takes a more compact form, easier to implement in the computations. These expressions are the complete ones. We have said that the intervolatile interaction term is negligible. Therefore, these two quantities are both 0. Furthermore, we see in the expression of the activity of water that there is a term which is multiplied by the amount of dissolved carbon dioxide. Therefore, in problems where only water is present, that is, when computing water solubility, that term entirely disappears. Similarly, in the expression for the activity coefficient of carbon dioxide, there is a term which is multiplied by the dissolved amount of water, and which therefore vanishes when computing carbon dioxide solubility. Instead, when dealing with mixed water-carbon dioxide saturation, both terms are present. Let's have a further look at this. The binary interaction coefficients involving water are not a function of pressure. Accordingly, the activity coefficient of water when dealing with water solubility, that is the case where water is the only volatile component in the system, is not a function of pressure. Conversely, when dealing with water plus carbon dioxide saturation, the activity coefficient of water becomes a function of pressure. The situation with carbon dioxide is different. The activity coefficient of carbon dioxide is a function of pressure always, even when carbon dioxide is the only volatile component in the system, whereas the presence of water together with carbon dioxide implies an additional term which is pressure independent. These aspects illustrate the complexities arising from real multi-component thermodynamics. The different components that distribute among the phases, in this case water and carbon dioxide, interact and affect each other in complex ways. The presence of carbon dioxide, whose activity coefficient depends on pressure, causes a pressure dependence also on the activity coefficient of water, which would be otherwise independent from pressure if carbon dioxide was absent. These kinds of complexities result in non-linear interactions and non-linear trends of water and carbon dioxide saturation when the two volatiles are both present in the system. One relevant example is reported in this figure, which shows computations made with the Solvcat code. The axis reports the dissolved amount of water and carbon dioxide for a given melt composition. The lines are isobars, with pressure reported on the lines in megapascal, and each isobar is shown for two different temperature values. On each axis, we read the solubility of each dissolved volatile. At any point not on the axis corresponds instead to saturation conditions, where the two volatile components are both present in the system. We see that at relatively low pressure, the normal trend for both volatiles is that the presence of the other one decreases its content at saturation. However, with increasing pressure, this trend can be disrupted, and the addition of water to the system can cause an increase rather than decrease of the carbon dioxide dissolved in the liquid. Well, we are at the end of the journey. My next slide shows the overall model performance, that is, the capability of the model to reproduce the database. Most of the data in the database are for water solubility, the first diagram on the top left. Water solubility in silicate melts has been studied for several decades, and the data are largely consistent with each other. In this case, only 9 adjustable quantities determined through regression are enough to reproduce a huge database with wide compositional variability. For carbon dioxide, the diagram in the center, the performance is still satisfactory, but the model parameters are more, and the database is much smaller than for water. Finally, water plus carbon dioxide saturation data are shown in the lowermost diagram in this figure, from which you can read the correspondence between the experimental pressure and the pressure determined from the model, both based on the experimental dissolved volatiles. The model is able to describe many features described from the experiments of the complex water and carbon dioxide saturation surface, such as the change from retrograde to prograde solubility of water in albedic melts with increasing pressure, the so-called alkali effect, consisting in a progressive decrease of water solubility with decreasing sodium content along the Albite K-feldspar join. The so-called plagioclase minimum, consisting of a minimum in water solubility at about half distance along the Albite anotite join. The progressive increase in carbon dioxide solubility with increasing degree of silica undersaturation. The high affinity of carbon dioxide with calcium, resulting in the ability of carbonatite melts to dissolve huge amounts of carbon dioxide even at atmospheric pressure, and many others, either revealed by the experiments or not yet illustrated experimentally. You are invited to check those code properties yourself. With the next lesson, Chiara will lead you through downloading the Solvecad code, which embeds all of the equations that we have seen throughout this entire training module. Chiara, we showed you how to create appropriate input files for Solvecad, run it on your computer, read the output and make figures and diagrams. And she will guide you through selected exercises, after which you will be able to continue with the code by yourself and employ it successfully in your research. What is most important is that you have reached so far in this journey. You can go back anytime and see any parts of these lessons repeatedly, of course, and make the exercise proposed so far if you didn't do it, if you didn't do them the first time. At the end, you will possess the knowledge and the skills required to be yourself a master in mixture thermodynamics. And you will be able to take it over and make the next critical developments yourself. And I'm looking forward to reading them in the international scientific literature.